Hi, welcome to eCircuit. Today I'm going to repair an Agilent E4440A spectrum analyzer. This is a 3 Hz to 26.5 GHz, and it's a really nice spectrum analyzer. I picked up this one from a dumpster ages ago, and it powers up, but it doesn't display the spectrum for certain frequency. I set it to 50 meg from here and 25 minus 25 dBm, and it doesn't show any signal here. So if I set the center frequency to 50 meg, span, let's say 5 meg, so there's nothing. I can change the reference level to bring the noise floor up, so I can't see nothing there. And also it shows that there is a numeric data error also, and if you go to the system, show an error, there's a lot of errors. So also have this calibration failed, align attenuation step at 40 dB step, so that's also failed. And also the before I noticed that there's a second local oscillator unlocked. So that's the first part we're going to have a look. Here we have the RF input into the first attenuator, and this is the IE14 on the schematic diagram, and it goes to the second attenuator, which is the attenuator B, which this one is the A15 of the schematic diagram, and then into the rhythm of the circuits and out into all this. So the local oscillator is the second local oscillator is on the A11 board, which is this board here, this particular board here. So on the schematic diagram here, and this is the block diagram, there's an input here. It goes into a 2 dB electronic attenuator. There's a 2 by 2 dB, and it goes into the second attenuator, which is there's a 10, 6, 20, and 30 dB attenuation here. So this one has a relays inside and into the rhythm, and we can follow the signal path here. And this is the first local oscillator. If we have problem with the signal in the first local oscillator, then we won't have any output here on the mixer. So the problem with this one, this module is the second oscillator. So we go into the second oscillator here. So the second oscillator is this part here. This is the second oscillator of this particular mixer of the A20 low band board or module. So it fails on the second oscillator, so that means I suspect that there's no oscillator or clock that's coming into this local oscillator here at J5 of A20, and this is coming from the A9 second low oscillator board, which is coming from all the way from the 600 megahertz frequency. So what I'm going to do is I'm going to see if we have 600 coming out of this port here, which is the W16 of the A11 reference board, and we're looking for a signal at roughly positive 13 dB plus or minus 3 dB. And also we have a look at also if there's a 300 megahertz at roughly minus 27 dBm output here. And this is just our reference because the 600 meg is coming from this 300 meg. It goes into a multiplier times 2, which is coming from the 300 megahertz filter here. So this is the main oscillator. So if we don't have a 600, if you have the 300, then likely we have the 100 megahertz voltage control oscillator here. It goes into an amplifier, and then it multiplies by 3. So that means the third harmonic of this one is used or filter. The third harmonics of 100 meg is the 300 meg, and then you filter it out and you'll have the 300 megahertz of frequency. Then the 300 megahertz of frequency, you have the amplifier, and then there's also harmonics of that 300 megahertz, which is the second harmonics. That's why they say times 2. So this is a way of making the first fundamental frequency to distort the fundamental frequency to generate harmonics. So the second harmonics here is filtered, and you have 600 megahertz, and then we have the amplifier, and it goes to this amplifier to make it positive 13 dBm, plus or minus 3 dB. And this is very important to have this certain signal here to drive for this A20 local low band module to work. So without the local second local oscillator, there's no output here, and then that's obvious that we also don't have the output on our spectrum display. So first is we're going to tap or see if we have 600 meg or 300 megahertz frequency clock. So this is the 300 megahertz of the A11 reference board, and this is the 600 megahertz output of the A11 reference board. So we're going to tap on the 300 first. We'll see if we have the 300 megahertz. Now we have the 300 megahertz tap into going into our spectrum analyzer here, and this is set to 300 megahertz. So we'll check for the peak, and peak marker it says is minus 29.4. So our 300 megahertz here is minus 27 dBm, which is very close. So we have a 29.4 dBm. So now we're going to check the 600 meg. Now we're going to remove this one, then we tap on the 600 megahertz. So here we still have the 300 megahertz here, which is this is the fundamental frequency, but it's lower amplitude at minus 34.85. Now we're going to change the frequency to 600 meg. So we have to reduce the reference level, amplitude, reference level, and then the peak. So we only have a 3.7 dBm, which is quite low. So we have definitely problem with the amplifier on the A11 reference board. So the required level is 13 dBm plus or minus 3 dB. So we are really out of that signal. So what I'm going to do is, so I'm going to inject 600 megahertz frequency at 13 dBm into the A11 600 meg coming out, and into the A9 second local oscillator board. So we're going to do that is we have this cable here, and we're going to inject this one. So I'm going to remove this one, and I just place this one into the 300 meg, so we can also monitor the 300 meg into the spectrum analyzer. The 600 meg, which is going into this module here, I'm going to remove this one. Okay, so that's from the 600 meg, and we're going to inject 600 meg 13 dBm signal here. Okay, I'm going to clear the error and then we're going to the frequency and 500 meg. Make sure we have the 500 meg, and we're going to, so we don't have that spike yet. We'll see if this one works. So we're going to system, alignment, and we need to align all. So we're going through the old alignments. So while the alignment is going, I'm checking the frequency here. We have the 50 megahertz, which is fed into the spectrum analyzer at minus 25 dBm. So we'll wait until the alignment is done, and we'll see if we have that waveform coming. Anyway, thanks for watching this video, and repair, and I hope you find this information useful. And here we go. So we have this signal here, it's coming. So if we check if we have this, okay, we're going to the marker. Where is the marker? Can you help me to find the marker? Here we go. So pick search. So we have minus 25.08 dBm, which is exactly the same as what we fed into the spectrum analyzer. We fed minus 25 dBm and we get minus 25 dBm at 50 megahertz. Now I'm going to change the frequency of the signal gen. So I'm going to change the frequency to 500 meg, and we'll see what the signal is. Okay, so since our frequency here is still in 50 meg, so we change the frequency to 500 meg. So here we go. We also have a nice waveform. So if you could change the video bandwidth, so if we change that one to at least 1 meg, yeah, 120 kilohertz, that's better. And then we change the span, make it smaller, yeah, that's better. So our peak is minus 25. So let's change the signal gen to the maximum frequency. The signal gen can only go up to 1.2 gigahertz, so we'll do that. Okay, sorry, this signal gen can go up to 2 gigs, so we set this one to 2 gigahertz. Now it's 2 gigahertz. Now we can change the frequency to 2 gigahertz, and we have it. So minus 26 dBm, it's just out by 0.1. There's a cable loss, and considering that it's already in a gigahertz, so we expect that there's a cable loss of 1 dB roughly, so that's what we get as minus 26. So still within specs, despite this signal gen is not calibrated. So it's doing the alignment again. So now we're going to check the system and check for error. So we don't have the second oscillator error, but we still have the aligned rough call gain, which is the 40 dB steps. So this is the problem with this one, is the attenuation of the input. So we're going back to the frequency, and we'll change the attenuation. We're going to the amplitude attenuation to manual. So we start at the very low attenuation. We'll see if that waveform will stay the same at minus 25, roughly minus 25 dBm. So we keep increasing 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. That drops. It drops 32. So I think all the way to 50. This will go up to 60 dB. Almost nothing there. So starting from 30 dB, it drops. So there's a problem on the attenuator. So we're going to analyze what would be the problem with this one. So to see what's the problem is, so what we're going to do to check that problem is, I'm going to change the signal frequency to, let's say, 500 meg, and then we're going to see what the output signal of this one here, which is the A14 of the schematic block diagram. So we'll have a look at what the output here. This one has two attenuation, which is the 2 dB, and the 2 dB, which is it switched from 0 dB, 2 dB, and 4 dB, which is if the 2 dB is on or the 2 dBs are on. So we're going to have a look at this one. So our input signal is minus 25, so we'll make it minus 10 dB, so we know how much attenuation we drop. First is we're going to remove this linkage, this RF linkage or connection between these two. Okay, so we'll connect our spectrum analyzer to here. So we'll set the frequency to 500 meg, and our amplitude level is negative 10 dBm. That's minus 10 dBm. Okay, so we have the 500 megahertz here, minus 10 dBm on the input of the amplifier, and we're looking on the signal from here down to the first oscillator, the first attenuator, and we'll see what the signal here. So we set this one, we set the frequency to 500 megahertz, and we have this nice waveform here. So we'll see what the peak level is. So we have 12 dBm, which is there is a 2 dB attenuator active on that. Uh, 2 dB active on the attenuator on the first attenuator A14. So what I'm going to do is I'm going to change the attenuation here. So this is how we control the attenuator. So we'll start from 6 dB. Okay, so 6 dB we increase. This is 6, that is 10. So there's no changes, it just fluctuates between 0, 2, and 4 dB. So I'll show you how this combination works on different attenuation. So we have 16 dB, 18 dB, 20 dB, 22 dB, 24 dB, 26 dB, 28, 30, still fine. So 32, 34, 36, 38, 40, 42. Let's go to 50 dB up to 60 dB. It's fine. So that means we conclude that the first attenuator A is working, or the A14 module is good. So we're going to check the second attenuator. So what we're going to do is we're going to connect these two, and then we measure from here, and we'll see what the output is. Okay, we're going to remove this one and we connect this one in here. Okay, so here we need to put this one back. Okay, so I'm going to remove this part here. This will be tricky to remove. Okay, and then we're going to connect the SMA. Okay, that's fine. We don't need to tie the one. We only need to see if there's a signal. So it's currently at 56 dB. We need to drop this down, this one down. Attenuation. So there's 48, 46, 42, 36, 34, 30, then 28. Then we have something on the 28 dB. So we need to increase our amplitude and our reference to see this one. So we have 39. We'll go down to 6 dB attenuation. So now we can see that from 28 to 30 it disappear. So we still have a little bit, but the attenuation between the 30 and 28 is a lot. So we only increase the attenuation by 2 dB and it drops by a couple of dB. So that's 28, 39, and it drops to 69, which is roughly 30 dB loss on that drop almost. So could be the 30 dB attenuator then, because it's very obvious that it drops from 35 to minus 35 to minus 65, so difference of minus 30 dB. Could be the 30 dB attenuator, but we'll find it out, and we are going to go through that steps. So we start with 6 dB. So this is a 6 dB. So our minus 10 minus 6 dB attenuation, we have a minus 17. So we'll keep increasing to 8 dB, 10 dB. So the 10 dB is minus 21, which is our drive level is minus 10. So it roughly drops by minus by 10 dB. So we'll keep going into 28. So that's 28 to 30. Now we know that there's a problem on the second attenuator, and this is the A15. So I'll show you what I have found. Okay, I'll show you what I've found. I'll go to the one that I have made, this one here. Okay, so these are the chart that I made. So this is the A15. So we're going to show you so this is the attenuator, input attenuator A. This is the input attenuator B, which is the A14, the A15. So the A14 composed of two attenuation, 2 dB and 2 dB. And the input attenuator B, which is the A15 module, consists of 4 attenuation, which is 6 dB, 10 dB, 20 dB, and 30 dB. And this is the output of the A15 on the W9 connection or connector. Let's show you this one here. Okay, so this is the attenuator A14. This is the attenuator A. So there's a 2 dB and 2 dB, 2 by 2 dB attenuators. So the A15 also composed of 4 dB attenuators. There are 10, 6, 20, and 30 dB, and this is a W9 output, and this is what we measured, and the attenuation dropped by 30 dB when it switched to at least 30 dB above. So now we're going back to my chart here. So this is my chart. So if at 6 dB, the 6 dB is on relay, and our W9 here is okay. So at 8 dB attenuation, the 2 dB and the 6 dB are on. Of the A14, 2 dB to A14 and 6 dB of the A15 are on, and they are still okay. So let's follow this one here. A15, 10 dB, the 12 dB is the 2 dB and 10 dB, and so on here. And look closely, everything here. So from up to the 28, what attenuators that was not present on here, which is we have okay output, and then when it's start from 30 dB, what attenuator was active when the attenuation start from 30 dB all the way up, and we don't have anything on the output. It's obvious, right? It's the 30 dB attenuator of the A15. So this is the problem. So because this attenuator, this module are very expensive, unfortunately, so I cannot afford to purchase the module. So I'm not sure if I could fix this one, but I know what's the problem, but I'm not sure if I could fix it because I can't purchase the module. It's quite expensive, and I get this whole system for free from the skip bin. So, and also we also have problem with the reference A11, so 600 meg. So the reference A11, it costs about 1,500 US dollar to buy this one, and the attenuator also, the A15 input attenuator B, costs also 1,000 US dollars to buy this one. Thanks for watching anyway, and in my next video I'll see if I could fix the attenuator, and also trying to fix the A11. The problem with the A11 reference board is there is a connection which is the ECE 40 pins connector, which is plugged into the main backplane, which is, I don't have that extension board or extension cable, so I purchased that particular connector of the A15. So I might use this cable to join, to just to solder on pin to pin straight through, so I could take this module out and see what I could do. Maybe there is a single transistor there or a monolithic transistor. This old might not have the monolithic, might have a single transistor to increase the output 600 megahertz to 13 dBm. So if I find that the transistor is faulty, I'm also not sure if we could source that transistor because this unit is quite old, and there's a slim chances that I will be able to fix this unit. So thanks for watching anyway, and I hope you find this information useful, and I'll see you next time, and bye for now.